Hey everyone, let's jump right into a really captivating mystery of chemistry and physics. Have you ever wondered why some liquids seemingly burst into flames the absolute second a spark gets near them, while others stubbornly refuse to burn, even if you hold an open flame directly to them? Well, today, we're diving deep into the hidden science of fire thresholds. We're going to strip away the myths and look at the precise metrics that govern how, when, and why things actually burn. Okay, so here's our roadmap for this explainer. We'll start with the literal spark of ignition, then break down the differences between flash, fire, and auto ignition points. From there, we'll look at solid fuels, compare open versus closed cup testing methods, and finally, wrap up with how all this translates into real-world safety standards. Let's get into it. All right, starting things off with a spark of ignition and what we call the vapor truth. So we really need to shatter a super common assumption right out of the gate. Just imagine dropping a tiny spark over a freezing cold puddle of gasoline. Now, imagine doing the exact same thing over a puddle of diesel fuel. Your gut probably tells you, hey, they're both highly flammable fuels, they'll both catch fire, right? But the reality is actually completely counterintuitive. Take a look at this. Gasoline has a flash point of negative 43 degrees Celsius. That means even at freezing temperatures, a spark is going to ignite it instantly. Yet, it needs to reach a massive 247 degrees to auto-ignite, meaning to catch fire without any spark at all. Now, diesel is the exact opposite. It heavily resists a spark. It needs an ambient temperature of over 52 degrees Celsius just to flash from a spark, but it spontaneously combusts at a much lower temperature inside an engine. So, why do we see such drastically different behavior here? Well, it all comes down to this absolute golden rule of fire science. And if you take away nothing else from this explainer, remember this. The liquid itself does not burn. The vapors do. I want you to really lock that concept in, because understanding that fire requires a flammable vapor cloud hovering just above the liquid, that's literally the linchpin for everything else we're going to talk about. If a liquid isn't emitting enough vapor to mix with the oxygen in the air, you simply do not get a fire, period, no matter how much you spark it. Okay, so that brings us to the escalation of heat, flash, fire, and auto-ignition points. Think of these temperature limits as a kind of precise staircase of danger. The very first step on that staircase is the flash point. By definition, this is the absolute lowest temperature where a liquid releases just enough vapor to momentarily ignite from a pilot flame. So, for example, if you have some kerosene sitting at 35 degrees Celsius, a flame does absolutely nothing. But heat it up to 62 degrees, and it produces just enough vapor for a quick flash of fire, but then it immediately goes out. It just can't sustain itself quite yet. Now, if we step just slightly higher up that staircase, we hit the fire point. This is where the liquid gets hot enough that vapor is being released at a sufficient, continuous rate. So if you heat that exact same batch of kerosene just 3 degrees higher, up to 65 degrees Celsius, it's now generating a steady stream of vapor. When you bring in your ignition source, it flashes, sure, but this time, the fire keeps burning. It sustains combustion for at least 5 seconds, even after you completely take away your match or spark. And finally, right at the very top of our staircase is the auto-ignition temperature. Now, this is the really wild part. At this stage, we don't even need a spark or a pilot flame anymore. If you heat that kerosene all the way up to around 220 degrees Celsius, it creates a chemical reaction so incredibly intense that the vapors just combine with oxygen and spontaneously burst into flames, purely from the heat, no spark required. Moving on, let's talk about what happens beyond liquids, looking at solid fuels and the flashover phenomenon.
You might be thinking this whole vapor rule only applies to liquid chemicals, but let's look at solid objects for a second, because the mechanics are actually shockingly similar. When solid materials, like a piece of plywood or, say, your living room couch, are exposed to high heat, they undergo this chemical breakdown called pyrolysis. As they heat up, they literally begin emitting the exact same kind of flammable vapors we just saw with liquids. Basically, solids have to turn into a vapor state to burn, too.
And honestly, this leads us to one of the most terrifying events in fire dynamics. It's called a flashover. Imagine a structure fire, right? You've got a fire burning over in the corner of a room. The ambient heat from that fire is baking the couch on the opposite side of the room. That couch is absorbing heat, undergoing pyrolysis, and releasing a massive, completely invisible cloud of flammable vapors. Once the overall room temperature hits that specific auto-ignition point, you don't even need a flame to touch the couch. The entire couch, and usually the whole room, will violently burst into flames in a split second. Those vapors were just sitting there in the air, waiting for that final heat threshold to trigger the whole shebang. So, how do we actually test for this stuff? Let's look at open versus closed cup methods for simulating these hazards. To understand how scientists safely measure these thresholds to protect us in the real world, we have to step into the laboratory. Specifically, we're looking at two fundamentally different methodologies, the closed cup and the open cup methods, and you absolutely cannot interchange these. The closed cup simulates confined spaces. Think of a sealed fuel drum. It traps all the vapors, which makes it highly sensitive and results in a lower, much more conservative flashpoint reading. The open cup, on the other hand, simulates exposed environments, like a spill on the ground, where vapors can naturally drift away. This yields a higher flashpoint. Testing incorrectly, like, say, putting a highly volatile liquid in an open cup, would let those vapors escape and give you a dangerously false, elevated safety rating. Now, this visual brilliantly illustrates how a closed cup test actually works in practice. This is the Penske-Martins tester. The mechanics here are rigorously defined. A sample is sealed up in a brass cup, it's continuously stirred at precisely 90 to 120 RPM, and it's heated at a strict 5 to 6 degrees Celsius per minute. Every degree or so, a tiny little shutter snaps open and a test flame is dipped directly into that captured vapor space to see if a flash occurs. It is an incredibly precise piece of equipment. But of course, science requires different tools for different extremes, right? On the left is that Penske-Martins apparatus we just talked about, which is perfect for standard fuels. On the right, however, is the Able apparatus. Now, this machine is specifically built to test highly volatile liquids that flash at incredibly low temperatures. We're talking all the way down to negative 18 degrees Celsius. To do this safely, the Able apparatus surrounds the test cup with a bath of corrosion-inhibiting ethylene glycol and water. That allows scientists to super chill the sample and then just slowly, carefully raise the temperature to pinpoint that critical freezing cold flashpoint. Of course, with lab tests this sensitive, human error is a massive risk. For example, testing volatile diesel with an open cup method, that isn't just bad science, it completely violates industry standards and literally risks starting a fire right there in the lab. Likewise, you can never, ever directly compare closed cup data to open cup data. They measure fundamentally different environments. Another really common error is mistaking a tiny blue halo around the test flame for an actual flashpoint. For a true flashpoint, the flame has to sweep across at least 75% of the liquid surface. And finally, if your sample is contaminated with water, you absolutely must dehydrate it first, often using something like calcium chloride. Why? Because otherwise, the water will turn to steam, completely mask the flammable vapors, and basically hand you a dangerously false pass. All right, let's bring it all together and talk about safety and hazard standards and how the rules actually get written. So, how do all these meticulous scientific definitions and lab tests actually translate into the laws that govern industrial safety? Well, regulatory bodies like OSHA, they don't just guess. They use the precise flash and boiling point metrics we've been talking about to sort liquids into 4 strict legal categories. Just look at Category 1 here, highly dangerous liquids with a flash point under 23 degrees Celsius. That classification dictates exactly how a chemical has to be packaged, stored, and transported globally. A simple lab mistake, say miscategorizing a Category 1 liquid as a Category 3, could result in it being loaded onto a truck without the proper precautions. And just like that, a routine transport turns into a literal ticking time bomb. A mere 5 seconds of continuous burning. That is all that physically separates the momentary warning flash of a flashpoint from the unstoppable self-sustaining combustion of a fire point. The margins we are dealing with here are just razor thin. Which brings us to the end of this explainer. We've seen today that the real danger isn't the puddle of liquid itself, is it? It's that invisible, highly volatile vapor cloud hovering just above it, just waiting for the right temperature or a stray spark. So I want to leave you with this thought. Knowing what you know now about how temperature actually dictates flammability, what everyday chemicals and unseen hazards might be quietly emitting invisible vapors in your garage or under your sink right now? Stay curious